Okay, so in this video, we're going to be going over a whole bunch of Fourier transform properties. Okay, so let me just write down our Fourier transform integrals here. So this is the inverse Fourier transform, where you're given a Fourier transform f of omega, and you want to obtain the time signal f of t. And also, if you're ever given the time signal f of t and you want to obtain the Fourier transform f of omega, you can use this one. Okay, so there they are. We'll be using those throughout the video. Okay, so let's just go through some properties. So the first one is linearity. Okay. And by the way, of course, you don't have to memorize all these properties. It's just good to know that, be aware of them, know that they exist, so that if you ever do recognize that you could use one, you could always look it up, of course. And also, any steps I take in proving these properties can be useful things to keep in mind for other problems as well. All right, so linearity, what does that say? That says if I have two functions f and t, or sorry, f and g, okay, and I make some sort of linear combination of them, okay, so a times f of t plus b times g of t, we could ask, what is the Fourier transform? And if f and g have Fourier transforms, capital F of omega and capital G of omega, as we write all the time, then the Fourier transform of this linear combination is just the same linear combination of the respective Fourier transforms. Okay, so this is something we actually proved previously. Okay, it was in the common Fourier transform pairs video, so I'm not going to do it again, but it's pretty clear. All you do is substitute this in to the Fourier transform equation. You break up the integral because the integral is linear into two separate integrals, and then you get these Fourier transform integrals as a result. Okay, so that's linearity. That's very useful. Let's look at another one. So this is the time shift property. And of course, some of these are going to look familiar to Fourier series properties that we've already seen too. So what happens when I take the Fourier transform of a time-shifted version of my function? Okay, so I'm going to take the Fourier transform f of t minus t naught, some time-shifted version. Well, I'm going to now do a change of variables because I want this to look like the Fourier transform formula, but you see I need the argument to f to be my integration variable. So I'm going to change variables to make that happen. So I'll let u be t minus t naught, the argument, and that means du is dt. And so what does that mean for this integral? That means I get f of u, e to the j, or sorry, negative j omega, and then what's t? Just bring t naught to the other side. T is u plus t naught. And then dt is du. Okay, now what can I do? Well, this e to the negative j t naught doesn't depend on the integration variable u, so I can bring it out. And I'm left with this integral, f of u, e to the negative j omega u du. And then sure enough, what is that? That is exactly my Fourier transform formula, just with u instead of t. But of course, that doesn't matter. You can use any integration variable you like. That whole thing is just f of omega. And so I get e to the negative j omega t naught times f of omega. Okay, so that's what happens when you time shift. You get this phase shift in frequency. And let me just summarize it. So f of t minus t naught has Fourier transform the same as f, big F of omega, but multiplied by this phase shift. Okay, so for a lot of these properties, there's going to be an analogous property when you do the same thing in frequency. So there's also a frequency shift property. And I'm not going to prove this because it's pretty much the same thing I just did. I'll start over here. What happens when I shift my Fourier transform in frequency? Well, I get my same inverse Fourier transform f of t, but then multiplied again by this frequency shift, but not negative this time, just j omega naught t. And I'll just write this is a similar proof as for the time shift property. Okay, so you can try that on your own for practice. It's almost the exact same thing. Okay, what's the next one? Time derivative. All right, what happens when I take the derivative of f of t? Okay, well, let's just use the inverse Fourier transform formula. Taking the derivative of f of t is the same as taking the derivative of this expression. All right, that was our inverse Fourier transform formula expression. Okay, so now I'll just bring the derivative inside the integral, f of omega. Now I have d dt e to the j omega t. Okay, the derivative of that, d omega, because this is the only thing that has a t in it, right? And I'm taking a derivative with respect to t. So what do I get? Well, I get f of omega, and then when I take that derivative, I get an extra factor of j omega. And now this right here must be the Fourier transform of this function, because this is the inverse Fourier transform formula, right? So anything that I put right there must be the Fourier transform of that function. Okay, so I'll just summarize that. So the derivative of f, and I take a derivative in time, in frequency, I get a factor of j omega. Okay. And just like for the time shift, we also have a frequency derivative. Frequency derivative. Okay, and again, it's almost the exact same proof. You can start with the derivative of f of omega, just like we did. And what happens in time? Well, similar thing, I have my f of t, and then I have a factor of negative j2. Okay, so again, I'll just write here, similar proof as for the time derivative. And you can try that on your own, almost the exact same thing. Okay, so that's a useful one too. So now let's look at what happens when we time or frequency scale. And you'll see why I'm grouping these properties together once we get the result. Okay, so what we're going to look at is, like we saw for Fourier series, we're going to look at f of at. We're going to scale the time variable. And let's start with when that scale factor is positive, then we'll look at when it's negative, and then we'll combine them into one nice expression. Okay, so let's look at the Fourier transform of f of a times t as time-scaled version of f. Okay, what are we going to do? Well, again, I want to eventually make this look like a Fourier transform, so I want that argument to f to be my integration variable. So we're going to do a change of variables. And just to make it, in the end, look a little more like t, I'm going to use tau this time, just so we can sort of recognize the Fourier transform form a little more easily. And so d tau is just going to be a dt. Okay, so what do I get? Well, when I am integrating from negative infinity to infinity, right, since a is positive, t is going to go, when t goes from negative infinity to infinity, when I multiply it by some positive number, tau is also going to go from negative infinity to infinity. Okay, I think even before when I did the change of variables, maybe I didn't mention that because we've done it so many times, but here, when t was going from negative infinity to infinity, right, when I subtract a constant, that doesn't change anything. U would still go from negative infinity to infinity. So that's how I got these bounds. Okay, similar thing here. When t goes from negative infinity to infinity and I multiply it by a positive constant, then tau is also going from negative infinity to infinity. Okay, so I'm going to have an integral still from negative infinity to infinity. Now f of at is really f of tau. And then e to the negative j omega, what is that t? You can see t is just tau divided by a. Okay, and then d tau is a dt. So dt is d tau divided by a. I'm just going to write the a out front, put the d tau there. Okay, so that d tau divided by a is just equal to this dt. Okay, so that's what we get when a is positive. Now, let's suppose a is negative. What happens then? Okay, so it's going to be pretty similar, but with one key difference, as you'll see. So we're going to start the same way. Now a is negative. We're still going to do a change of variables. Okay, and tau is still going to be a times t. D tau is still going to be a dt. Nothing changes there. But now, what about these integration bounds? Okay, now a is negative. Maybe it's -3. Well, now when t starts at negative infinity, when I multiply by -3 times negative infinity, I get that tau is at positive infinity. And when t goes up to infinity, a is like -3, just to take an example. Well, some negative number times infinity is going to give me negative infinity. Okay, so those are the bounds I get with this particular change of variables because a is negative. Okay, but then f of at, well, at is certainly still tau. And e to the -j omega, well, t is still tau divided by a. That hasn't changed. That's still good. And now dt is still going to be d tau divided by a, so I'll keep that. Okay. But now, of course, I don't like these bounds being backwards. So as you remember from calculus, if I ever want to switch my integration bounds, I just have to add a negative sign. So I'll add that negative sign right there. And I go negative infinity to infinity. F of tau, e to the -j omega, tau over a, d tau. Okay, so you can see that this is what we get when a is positive, and this is what we get when a is negative. They're exactly the same, except for this a and negative a. Okay, so we're going to use that right now. So in both cases, okay, whether a is positive or a is negative, we can write what we get like this. Okay, so we have the integral. What do we start with? The integral from negative infinity to infinity, f of at, e to the -j omega t dt. That's what we started with in both cases. And so what is this going to be equal to? Well, certainly the second part, this integral, is the same, the exact same in both cases. Right? That part is the same in both cases for sure. But now what happens to that coefficient? Well, when a is positive, I get a. And when a is negative, I get negative a. So what does that look like? When a is positive, I get the function a. When a is negative, I get the function negative a. Well, look at that. That's absolute value of a. That's exactly what absolute value of a does. When a is positive, absolute value of a just equals a. When a is negative, absolute value of a equals negative a. Right? That's exactly what absolute value does. And so I can just write 1 over absolute value of a. So it's a nice little trick to combine both of those cases into one concise expression. And now what do we have here? Well, let me just rewrite this exponent. Let me rewrite this exponent a little bit. Let me group the divided by a with the omega. I'm going to write this as omega over a times tau. Right? I just took this divided by a and sort of just grouped it with the omega. And now we can see that this is exactly the Fourier transform of f, just evaluated at omega over a. Right? This is exactly the Fourier transform, except if I were to plug in omega over a, I would get an omega over a there. So integral of f of t e to the -j omega over a t dt. And that's exactly what I have here, omega over a. And then, of course, it doesn't matter whether I use t or tau, but this is f of omega over a. And so all in all, we get 1 over the absolute value of a times f of omega over a. Okay, so I'll just summarize this. So when I time scale by some constant a, okay, and a is not 0, okay, so I'm actually time scaling, then what do I get for the Fourier transform? I get 1 over the absolute value of a times f of omega over a. Okay, so you can see that time reversal is a special case of this. Maybe I'll put the a not 0 on this side. Time reversal is a special case where I just let a equal 1. And I'll say maybe in particular, I'll just say a special case. Okay, f of -t, time reversal. What do I get? Well, the absolute value of -1 is just 1. So I just get f, and then omega divided by -1 is just negative omega. Okay, so we get time reversal as a special case. Okay, so that can be useful too. All right, let's keep going. So what happens with conjugation? Okay, well, to do this one, I'm going to look at f conjugate of negative omega, and we'll just see what we get. Okay, so what do we get with f conjugate of negative omega? Well, we're going to just get the Fourier transform of f of t, but evaluated at negative omega, and then conjugate the whole thing. Okay, so this right here is f of negative omega. I just took the Fourier transform formula, plugged in negative omega, and I'm conjugating the whole thing. Let's see what we get. Gonna get the integral of f conjugate of t. And now here, the negatives cancel, so I get e to the j omega t. But then when I conjugate, I get an extra negative, e to the negative j omega t dt. And what do you know? This right here is just the Fourier transform of this guy, f conjugate of t. Okay, so we just kind of manipulated this formula a little bit to see that the Fourier transform f conjugate of t is f conjugate of negative omega. Okay, so I'll just summarize that. F conjugate of t as Fourier transform. Here's the Fourier transform formula, and we get that expression, f conjugate of negative omega. Okay, so that's what happens when you conjugate a function. That's how the Fourier transform changes. Now let's look at the property that is conjugate symmetry. For real signals. Okay, so what happens when I happen to have a real valued signal, f of t? Well, what does it mean to be real? That means that f of t equals f conjugate of t. And that's what it means to be a real number, that you equal your complex conjugate. Okay, we saw that in the complex numbers review video. What does that mean for the Fourier transforms? Well, if those two functions of time are equal, then their Fourier transforms have to be equal too. Fourier transform of f of t is f of omega, and the Fourier transform of f conjugate of t, we just saw, is f conjugate of negative omega. So that means those two functions are the same. And that's all this property says. So if f of t is real, then that implies, most people write it like this, that f of negative omega, we can just negate both of these omegas. F of negative omega, then, what happens when I negate the argument of the Fourier transform? If f of t is real, I get the conjugate. Okay, so that's known as conjugate symmetry for real signals. Okay, we saw a similar thing when we were talking about the frequency response of RLC circuits way back at the beginning of the class. We saw a similar conjugate symmetry property. Okay, so now we can look at the Fourier transform of real and even signals. Okay, what happens then? Well, we can use the realness. If f of t is real, then we just saw f of negative omega equals f conjugate of omega. And if f of t is even, what does that mean? Well, that just means that f of t equals f of negative t. It equals itself when I flip it across the vertical axis. And so now I can say that if those two functions of time are the same, their Fourier transforms have to be the same. This is f of omega. When we saw this time reversal property, that's just f of negative omega. Fourier transform f of negative t is f of negative omega. That's what I get there. Okay, and what does that tell us? This tells us that f of omega is even. All right, that's what it means to be even. When I negate the argument, I get back the same function. Okay, and also, we can see that f of omega equals f of negative omega from this property. But then finally, we use this, f of negative omega equals f conjugate of omega. Now we get that f of omega equals its conjugate. Well, we just said that means that f of omega is real. Okay, so using f of t being real and even, we get that f of omega is also real and even. Okay, so that's the property. So f of t, real and even, implies that f of omega is real and even. All right. Only a couple more here. So what happens when we look at the Fourier transform of real and odd signals, you might be asking. Okay, well, I'll let you think about this. It's almost the exact same as we just saw. F of t is real and odd. It turns out that means that f of omega is purely imaginary. And odd. Okay, so I'll just say similar proof as above. Okay, it's going to be almost the exact same reasoning. It's just instead of getting real and even, it turns out you're going to get purely imaginary and odd. So I'll let you think about that on your own as well. All right, so the last one isn't quite the same style of property, but it's just a couple useful things to know. This is sometimes known as the DC value in time or frequency. And we've already seen this, I think, a couple times in other proofs, but all this is saying is what happens if I look at sort of the DC value when omega is 0. In other words, when there's really no frequency, it's just like a constant DC value. There's no alternating aspect to this. It's just when omega, the frequency is 0. And we can just use the Fourier transform formula and see that this is the integral of f of t, e to the negative j times 0 times t, right? Just plugging in 0 for omega. And so we get that this is the integral, actually, of the function f of t. So we've used this already a couple times in previous videos, but here it is explicitly. If you ever want the integral of your time function and you happen to have the Fourier transform, you can just plug in omega equals 0. And there's a similar one for plugging in 0 to our f of t function. And we're going to do the same thing. This is f of omega e to the j omega times 0. Just plugging in 0 for t in this inverse Fourier transform formula, and we just get 1 over 2 pi integral of f of omega. Okay, so these two can be useful sometimes for, solving various problems or proving things, as we've seen. So I just thought I'd include them in this video. But okay, so that was a lot of properties. Hopefully you are getting more comfortable with the Fourier transform and inverse Fourier transform. Again, you don't have to memorize all of these, just good to be aware that they exist. So if you happen to encounter a problem where you realize one might be useful, you can always look it up. And hopefully some of the steps we made in this video are useful for solving other problems as well. Okay, so that's all I had for this video, and I'll see you in the next one.